All right, so today I'll give you a short lecture and introduce one more topic and also keep giving you another another few assignments. But hopefully these will become easier, especially if, like I said, if you can get the PCA one done, then these are basically enhancements or refinement of the similar idea. So what I wanted you to be able to get the general idea is that anytime we do object recognition, which is one of the key concepts in computer vision, typically there are two steps involved to it. Okay, there's some kind of a registration step. So there's image registration. Okay, then after we have aligned whatever we are looking for, and before image registration, okay, we have a step called object detection. So we detect, for example, a face or a car or whatever, right? Then we further rotate it, straighten it out, scale it, and then we feed it to our recognition system and then do the recognition, right? Okay, so right now we've already looked at this in detail, but I'll come back to it and show you the deep learning approach to image registration and deep learning approach to, we have our classical way and deep learning based approach over here. So we developed the math behind image registration. So remember once we had the transformation matrix that we developed in terms of A, B, T1, T2, which is the shift in X, shift in Y, A, B take care of the rotation scaling of the image. So you guys have a decent idea of this one. Now we are looking at the recognition approach, right? So the recognition approach, again, classical, modern approaches and so on. So one of the very popular ones that is, of course, a PCA. So as an example, in the last assignment, you guys did the face recognition, or hopefully will be able to complete it soon. And you guys saw on the AT&T data set, we are able to get close to 90% or slightly greater than 90% accuracy, right? Okay, so then as we discussed, the concept over here was that PCA, if this is our data, it does not distinguish what category the data belongs to, what class it belongs to. It tries to create a projection so that there's a maximum distinction between the data, which works well, but it's not good for classification. So this is where we looked at the LDA approach, linear discriminant analysis, where by creating between class matrices, scatter matrices, within class scatter matrices, and then based on the eigenvalue, vectors of these, we can come up with C minus 1, C is the number of classes, projections, so that we can distinguish the data by class, by category, as much as possible, right? Okay, so this is your next assignment. Hopefully, once you do it, you'll be able to see a tiny bit better accuracy compared to over here. Then, now let's take a look at third approach, which is based on deep learning. So first, now let's take a look at based on neural networks and deep learning. How will this work out? Okay, so one idea was that we use, so again, this goes into a couple of categories. We use autoencoders. So use autoencoders to do nonlinear PCA. So internally, autoencoders accomplish what is called the nonlinear PCA, meaning it will do similar to what this is doing, but without worrying about the strict linearity of our axis. Like I said, surface could be, one surface could be like this, the other surface, as long they'll still be orthogonal, but data doesn't have to be completely in linear format. So obviously this is better than a PCA. So we'll try that. And we talked about in the deep learning class about this one. So very briefly. Okay, so to accomplish this part, this is what you will do. You'll create an autoencoder neural network. Okay, an autoencoder is basically a neural network with number of inputs equal to number of outputs. So basically, it compresses the data. Then it decompresses the data. So this is our input. So there will be set of weights over here, set of weights over here, but the number of inputs here is exactly same as number of inputs. So once we train it, we, for example, will give it some face, and of course we'll linearize it. Okay, so remember in our AT&T data set, this was 92 by 112. So we'll linearize it, we'll feed all of this over here. Okay, then we'll divide everything by 255 because typically with neural networks, the input data to the network is scaled between 0 and 1. So the expected output will be same as input. So in other words, what we are trying to do is we are trying to make our network learn how to compress, what is the best compressed representation of the input data. Okay? So for example, if we have 100 neurons over here, as we train it on many, many pictures, we give it an input, expected output is the same. We give it another one, right? So for example, if we are operating on the AT&T data set, which is very small, and the reason I picked AT&T data set is so that you guys can run it very easily on your laptops. Otherwise, if we take a look at, for example, there's a data set called LFW with, I forgot, 1.3 million faces. It will take forever for you guys to coming back over here, in our case, our training data will be 40 persons, 5 for each, so 200. So you'll train it on, give it 200 pictures, expected output, each one is the same. Okay, because the code for this, you guys did it in C#, or even if you haven't done it, you perhaps will be doing it in C#. So I'll give you, in case you haven't taken the deep learning class, I'll give you the code in C# for creating a neural network. Okay, so you can just modify it slightly so that expected output is the same as the input, and you can easily train this network. So then once it's trained, what you will do is you will remove the decompression part. So only this part will be kept. So, okay, so after network is trained, and this is the autoencoder I'm talking about. Okay, then remove decoder part. So in other words, only this part will be kept up to this point. Okay, so
for the nonlinear PCA.
yes. Okay, so you will remove the output layer from the neural network, and whatever weights you had learned from here, you will keep those weights. So keep learned weights. Okay, so now as you can see, what it is doing is taking, for example, a 92 by 112 linearized image. And for example, if we have 100 neurons over here, exactly like a PCA, it is giving us 100 projections, but in this case, it's on the nonlinear dimensions, not the linear dimensions. Okay. So this data that we get out of the autoencoder, this is basically similar to applying nonlinear PCA, right? But in our case, we want to do recognition, right? So then what you will do is, remember this is just a neural network, and I'll give you the code for a regular neural network. So all you have to do is attach it to another neural network with the output layer. Sorry, you will do or we can do a hidden layer also. We can do a hidden plus output layer. Because the purpose of this is to do the classification, okay? So for example, you can put 50 neurons over here in the hidden layer. Okay, the question is, how many neurons will you put in the output layer? If you're operating on the AT&T data set.
10.
No. How many faces did we
Sorry,
have?
40, right?
40?
40, because it was 40 different people, because it has to tell us which input image belongs to which person. So output will be 40, right? What if we wanted to also make it such that if it is none of those 40, it also should flag us? In that case, what would we do? Make it 41, okay? So anyway, so then you will test the accuracy of it. And like I said, setting this up is literally not more than an hour's work, because like I said, I'll provide you the code for creating the autoencoder. And it's the same code over here that you are putting over here and retraining it. So you retrain the whole thing so that it will go and basically slightly adjust these weights. So once we attach this, then you allow these to be adjusted. So their initial weights, are coming from training the autoencoder. Then we do a full back propagation so that we can adjust all of these. Okay, so this will give you an idea. So essentially, think of it this way. This part, the autoencoder is giving us the features, and then hidden layer plus output layer is capable of creating a nonlinear decision boundary. So this is basically able to do the classification in any of the 40 categories. So then your job will be to compare with the previous approaches to see how good or how bad it is. Okay. Okay. So
you have to train twice?
You have to train it twice, correct. First, the autoencoder training, then you remove this part. Whatever weights are will be kept as the initial weights. Mm-hmm. Then you connect to this layer, a hidden layer and an output layer, and train it now again on the 200 data set. But what type of activation function will you use over here? Softmax, because we are doing a multi-class classification. Okay. And this will be ReLU. That usually works the best. And here, it doesn't matter, you can pick sigmoid or ReLU or whatever. probably really will be better in my opinion. So anyway, that's your next enhancement after the LDA. Okay. So then the following assignment, let me describe to you. But again, the idea is by the time you're done with this course, okay, any topic related to vision you should be fluent in, okay, and be able to understand it, why we are doing it, what's the purpose. Okay, so then there's, as far as features are concerned. Okay, so once again, the general idea in recognition is whatever input we give, we extract features, and then we feed it to a classifier. And so this could be, for example, a neural network, could also be a support vector machine. If I have time, I'll cover the background on the support vector machine, but usually a neural network will do a better job than a support vector machine, so that's why, but anyway, so any kind of classifier, most of the time, like I said, this will be with one hidden layer, one output layer, so that it can learn any nonlinear decision boundary, right? Okay, so features, as we saw, these features could come from PCA, correct? Or what else? LDA, or what else? Nonlinear PCA, meaning autoencoder. Right? Okay, so all of these are basically transforming the data from a pixel domain to a complex domain, right? Like in the eigenvalue, so both of these are eigenvalue based. Okay, autoencoder is also doing a nonlinear PCA, so it is sort of equivalent of moving from regular Euclidean domain to, for example, an eigendomain. So all three of these are doing those things, right? Now, in some scenarios, there's another technique which works better, okay? And that is called texture-based.
What would be just an overall general example where those first three would not do the job and that you would need to go to that?
Depending upon, see, texture is basically like where the surface color or the
I see.
like the smoothness of the surface matters a lot. So that's where usually the texture comes, because it's focusing on the surface, not so much as the relationships of other things. Okay. So anyway, I mean, to some extent, as we put it together, it will also be taking a look at the relationship of other nearby things, but you'll see how it's done. But it is focusing on the actual relationship of the pixels to pixels on the surface, basically. Okay. Anyway, so it's a very, very simple technique. And the techniques is called local binary patterns, short as LBP. Okay, so it's like I said, very easy, very simple, very popular technique. So, so we will also try to do face recognition using LBP so that we can compare with the previous approaches and see how well they do. Okay. Okay, so what's the idea in LBP? Okay, so here, easiest way is, suppose you're given an image. Let's take a look at a grayscale image, 5, 50, 80, 30, 40, 90, 10, 20, let me make it 60, 70, 10, 15, let's make it something like this, right? So let me pick some numbers. So pretend this is the grayscale image, and these are the pixel values, okay? So in local binary pattern, just like convolution, what we do is we take a look at, for example, a 3x3 window. Okay, and then in this 3x3 window, around the center pixel, so we compare the center pixel with all the neighbors. And we start from one end. For example, we can start over here. Okay, and we compare each pixel to the center pixel. If the value is smaller, we'll put a 0. If the value is bigger, then the center pixel will put a 1. So if you take a look at how many neighbors of the center pixel are there, 1, 2, 3, 4, 5, 6, 7, 8. 8 neighbors. So we'll basically produce an 8-bit binary number, starting from here, comparing, and finishing over here. Okay? So is 50 greater than 60?
0, 1, 0.
So will be 0. Then we go to 80. 80 greater than 60. Yes? 1. 30 greater than 60? 0. 70 greater than 60? 20 greater than 60?
No.
Yes. No. So this is basically what we call LBP at this particular position. This is the local binary pattern. Right? So after we are done with this, then what do? We move the window to the 3x3 window, 1 pixel to the right, and do the same thing. Now, we compare everything to 70. So 80 compared to 70, 1, right? So again, we'll start from here and go in a circle. 30 compared to 70, 0. 40 compared to 70, 0, 0, 0, 0, 0, 0. So this will be the LBP in this position. Everybody agrees? Okay. So suppose I gave you 30 by 30 image. Can you tell me how many local binary patterns will we get? 28 by 28. Remember, you're putting a 3 by 3 window, you're moving it 1 pixel, the last position will be over here. First position was right in the second row, second column. So essentially there will be 28 by 28 local binary patterns. Okay, so now let me ask you another question. How many different patterns can we get? So basically, number of different patterns.
2 power 8 minus 1.
2 to the power 8.
2 to the power 8? 256, right? Because each pattern is 8-bit, so obviously, so then what we do further is divide each LBP in 2 categories. Okay, what are those categories? We call them uniform and non-uniform. Okay, so what exactly is a uniform pattern? Uniform pattern is where maximum of 2-bit changes occur. In an LBP. Okay, what is a non-uniform pattern? Greater than 2-bit changes. Meaning 3 or 4 or 5. Okay, so let me give you an example. Okay, suppose you have a pattern like this. Oops, one extra 0. Okay, so take a look over here. Is this 0 changing to a 1? So we count it as 1 change. then 1 changing to a 0. 2 changes, 0 to a 1 again. 3, 1 to a 0. And we also take a look at the circular change. So in this case, how many changes occurred? 4. 4 changes. So is this a uniform pattern or a non-uniform pattern? Non-uniform. So this is an example of non-uniform pattern. Okay, let me give you another example. Suppose I gave you okay. Okay, so now let's take a look over here. How many changes are occurring? 1, 2. Any change in the circular? No. So this is 2 changes. So what kind of pattern it is? Uniform, right? Okay, by the way, what if I had 1, 0, 0, 1, 1, 1, 1, 0? Yeah, so 1, 2, 3, and then further over here.
Correct.
4 changes over here, so this is non-uniform, right? Okay, so it turns out if we examine the data for a lot of images, okay, something like greater than, I forgot, 90% of patterns are uniform. Okay, I don't remember the exact percentage, but it may be even higher. Okay, so typically what we do is we ignore these non-uniform patterns. Not totally, but I'll explain as we go into the implementation details. Okay, so it turns out how many total patterns are possible? 356, right? If we go through and examine all of these, we will find out that only 58 patterns are uniform. Okay, so that means more than, or 100 and, what would it be, 188 patterns. No, 198 patterns. 198 are non-uniform. Okay, but non-uniform occur very rarely. So that's why we just focus on 58 patterns and not worry about the non-uniform patterns to an extent. Like I said, I'll explain again. Okay, so now let me show you how we will create local binary based features over here. Okay, so now we will have LBP based features. Okay, so for example, we take a look at a 100 by 100 pixel. Let me to easily understand it, make it 102 by 102. And let's pretend we were doing face recognition. So can you tell me how many local binary patterns will we get out of these?
100.
And what's that number?
10,000.
10,000, right? So there will be 10,000 numbers that we will need to feed to the classifier, okay? What if we did not do local binary pattern, fed just the pixels? Will that number be any significantly different?
No, but just slightly.
If I just fed the pixels, right? Won't it be 102 by 102? Which is very similar to, or, I mean, approximately 10,000, right? So So just feeding the LBP is not the proper way to do it. So what we do it, like I said, 90% of these features are non-uniform as far as LBP is concerned, right? Okay, so what we do is, okay, so here's our case. Okay, so again, let's pretend this is 100 by 100. Okay, so what we do is we divide this into further a grid of 5 by 5 as an example. So if I divide it into a grid of 1, 2, 3, 4, 5, okay. So what will be the size of each one of these as an example?
20 in one, yeah, 20 by 2, correct.
20 by 20, right? So now let me compute the LVP features over here. How many LVP features will there be in the, or it's not features, let me just call it local binary patterns in this 20 by 20? In this 20 by 20 cell?
18 by 18.
18 by 18, correct? Okay, which is still, you know, more than 300, I think, right? Whatever that number is. Okay, so then what we do is, out of these 18 by 18 LBP numbers, we create a histogram. Okay, so remember a histogram is just a count, frequency count. So here pattern 0, pattern 1, or let me just go 1 through 57, 1, 2, or 1 through 58. Okay, so what's this exact number? 64, 4, 324, okay. So 324 patterns. So obviously some of these will occur more than one time, right? So let's say pattern number 45 occurs 5 times. Pattern number, I don't know, 51 occurs 3 times. So some patterns will occur more, some patterns will occur less. So we'll basically create a histogram of these. Okay, so as you can see, if I express it as a vector or as a 1 by n matrix, so let me make it. So this will be 58 by 1 vector. You guys agree? Okay, so there will be some numbers like 0, 0, 5, 3, 2, 0, 6, 0, 9, and so on. Okay, so again, this is the count of a particular pattern that appears. Okay, so to summarize, out of